Okay, in this lecture I'm going to be talking to you about complex numbers and exponential functions, sine function and cosine functions, and how these things are all interrelated. So in this course and in many other physics courses you'll find that we use complex numbers fairly often, even though the imaginary part of the complex number is often not part of the real physical description of some phenomena. So I remember when I was at your level of physics and being utterly confused by complex numbers and why anybody would want to introduce these things in order to explain real phenomenon. But it turns out they can be very useful, and they are used all the time in physics. So if this is your first exposure to it, you might as well get started and get used to it, because it's an important mathematical tool in physics, and we'll use it in this course fairly often. In fact, we've already seen it. The solution to the pendulum problem was already a complex number. And I'll actually get to that in this lecture. I'll come back to that complex solution to the pendulum problem and show you exactly how that's related to the oscillatory motion that we know that a pendulum actually is doing. Okay, so our topic is complex numbers, the exponential function, the sine function, and cosine function, and how these things are related to each other. Okay, but just to start off with, we're just going to review some very basic stuff about complex numbers, just in case you haven't had much exposure to these ideas. So, and it can't hurt to review them if you are rusty. So let's just recall first that a complex number is just a number with a real and an imaginary part. So it has a real part and an imaginary part. This is the mathematical jargon that we use to describe the two parts, and we often, so if you have a complex number z and it looks like this, x plus I times y, where x and y are real numbers, then the y is the imaginary part here because it's multiplied by I, where I equals square root of -1, of course. So that's the very basic complex number there. So this is the real part, and this y is the imaginary part. Okay, so now if we take a look at this, one common way to think about and graphically learn some things about complex numbers is to look in the complex plane. So the complex plane is just a two-dimensional plane where one axis is the real axis and the one axis is the imaginary axis. And say z is some number sitting out here, and that is sitting at the point where the real part is x and the imaginary part is y. Okay? So another way to describe a complex number other than the real part plus I times the imaginary part is as follows. So you can describe this point, it's the same imaginary number, you can describe it with a line from this origin to the point, which is of length r, and the angle theta, which is between the real axis and that line of length r. Okay, so once you have that information, you can start writing down some additional facts. For example, you know that r squared is equal to x squared plus y squared. That's one fact. You know that, just some more facts here, tangent theta is equal to the ratio of x over y, and sine theta. We're going to use some of these facts a bit later, just in case you're wondering why I'm writing them down. Okay, so those are all true statements. And if with these statements in hand, then we can rewrite z. So these things imply that z is equal to r cos theta plus I r sine theta, right? Y is equal to r times sine theta, x is equal to r times cosine theta. Therefore, you can rewrite z in this way. Okay, so that is just a very, very brief introduction to what a complex number is and two ways to represent it. And now we're going to switch now to talking about exponential functions whose arguments are complex numbers. Okay, so let me erase this for now. Okay, so if you didn't see the online, or you didn't watch the online lecture yet about Taylor series, you should do that. I'm going to reference now what we learned in that lecture. So this is, what I'm going to write down now is the Taylor series expansion for e to the I theta, where theta is a real number and I is square root of negative 1. So Taylor series of e to the I theta is what I'm going to write down. And as always, when you say we're going to do a Taylor series of some function, we're going to be talking about the Taylor series of that function near a particular point, and that's near the point where theta equals 0. Which is typically what, if people don't specify what point they're going to be doing the Taylor series near, they usually mean 0. Okay, so the Taylor series of e to the I theta is, well, as usual, we start out with the function itself evaluated at the point you're talking about, evaluated at 0. And then we add in the second term is the first derivative of that function, so that's I e to the I 0 divided by, divided by 1 factorial times theta minus 0. Just writing out that formula for the Taylor series in all of its details here, even though a lot of these things are zeros and ones. So the next term is the second derivative of this function, so that brings down 2 factors of I. Oops. We'll go ahead and simplify this in a moment, but theta minus 0 squared over 2 factorial plus, plus I cubed e to the I 0 theta minus 0 cubed over 3 factorial plus I to the 4th, da 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 da. This keeps going. Okay, so let's simplify this. This is 1 plus I theta e to the I 0 is just 1 plus, well, I squared is minus 1. So we've got minus theta squared over 2 factorial. Got I cubed, that's minus I. And now we have theta cubed over 3 factorial. I to the 4th, that's minus 1 times minus 1, so plus 1. Theta to the 4th divided by 4 factorial. And we keep going. The next term is I theta to the 5th, 5 factorial, minus I theta to the 6th, 6 factorial, minus theta 7th over 7 factorial, dot, dot, dot. Okay, so the next thing I'm going to do, whoops, I think I got one thing wrong here. This is just, there we go. so now the next thing I'm going to do is take this Taylor series of e to the I theta and break it into its real terms and its imaginary terms. So first, let's write down all the real terms. So this thing is equal to 1. Here's a real term. This is an imaginary term. So we'll save that for a little bit later. Imaginary, real. Imaginary, real. Okay. Now let's write down all of the imaginary terms. So factoring out the I, we have theta, and then the next imaginary term is this guy, minus theta cubed over 3 factorial, and we have plus theta to the 5th over 5 factorial, minus theta 7 over 7 factorial. Okay, so these are just all of the real terms here grouped together, and all of the imaginary terms grouped together. And if you saw the lecture, the online lecture that I gave about Taylor series, you'll recognize immediately that all the real things here are the Taylor series of cosine theta. So all that stuff is cosine theta. There are more terms in cosine theta, but those are the first 4 terms in cosine theta. And so if we took all the infinite number of terms in this sum, it would be equal to cosine theta, and plus the imaginary parts are sine theta. So there you have it. This is a fundamental relationship between e to the I theta and the trig functions cos and sine, if you consider imaginary, the Taylor series of e to the I theta, where I is imaginary number. Okay, so this is an important thing to know, and you should just go ahead and commit it to memory if you don't know that relationship already. And now, another point that I would make is that in the last board that I erased, I wrote down that one way to represent an arbitrary complex number is just r e to the I theta. All right, this is an arbitrary complex number whose distance from the origin of the complex plane is r, and its angle from the real axis is theta. So if you think of it that way, then this arbitrary complex number can be written as r cos theta plus I r sine theta. Whoops, actually realizing what I said now. This is actually what I wrote down before. This is what I showed you first. That was just based on the geometry of the complex plane. And now, given this relationship, we can now realize that any complex number can be written in this way, r times e to the I theta. Okay, that was one of the points I wanted to make. Okay, so now we're going to take this little bit of knowledge about complex numbers, exponential sines and cosines, and just bring it back to reality a bit with the pendulum example. Okay, so let's go back to the pendulum example. I'm just going to start from the solution we found during the first lecture in class, not an online lecture. So in class, we solved it. We solved the pendulum problem for small angles. So a pendulum with small angle motion has the solution. So let me just draw the picture just to remind you. Have x, y, and we've got some pendulum here. swinging back and forth. And as long as this angle here is small, then we're talking about the small angle motion solution here. So as long as that angle is small, then what we can say, and what we found in class, is that the x component of the trajectory of the pendulum, as it's going back and forth as a function of time, is equal to some initial position from which the pendulum was released times this e to the I square root g over L. So the length of this guy is L, and gravity is, the solution is e to the I square root g over L times t. Now, if we want to rewrite that, we can rewrite it in terms of sines and cosines, given what we now know about the relationship between e to the I something and the cosine sine function. So this is x naught times cosine of the something, g over L times t, plus x naught I times sine of that something, okay. So this is just rewriting the exact same solution. And the point is that, well, one way to describe the motion of this pendulum is to think about it in terms of the motion of this trajectory in the complex plane. So if we think about the real part of this x of t versus the imaginary part of x of t, then what that gives us is a circle, a circular motion, because we're talking about time in here. So we have circular motion. The radius of that circle is exactly equal to x naught. And the frequency at which we're going around this circle, this is oscillatory motion, so we're going around the circle at a rate where this angle here, theta, is changing at exactly this rate. Right? So theta, in other words, what this formula is telling you is that theta is equal to square root g over L times t. Therefore, you take one time derivative and you get g over L. So the rate at which we're moving around this circle is square root g over L. Therefore, that is the frequency, the angular frequency that this pendulum is swinging back and forth with, oscillating with. So that's the view of the pendulum motion in terms of the complex solution, and the view in the complex plane. But you can always, and equivalently, you can think of it in terms of the real part of the solution. So an equivalent solution to the equations of motion for the pendulum is just the real part of x. So just this part. So you could write that down if you want. This is, so the imaginary part is something that comes out of doing the math, and it doesn't hurt anything. Sometimes it buys you some power in terms of the math, but it doesn't hurt anything to throw that part away. And if you really want to know what's happening to the pendulum, you can always take the real part of the solution. So an equivalent solution is just the real part. So, which is just, obviously that's just an oscillatory function. So in this case, if we plot x versus time, it's just this function, where the initial height here is at x naught, and this gets down to as low as minus x naught. And the period of this motion is, so that period there is 1 over this frequency. So one cycle happens in square root L over G. time. Okay. So I think that's all I'm going to say about complex numbers, sines and cosines, exponentials. But you'll see this happening a lot during this course because we'll talk a lot about solving problems where there's oscillatory motion, and often that is accomplished using these sort of solutions that involve exponential functions of complex numbers.